Okay, then next thing we will talk about is least upper bound. Suppose there is a partial ordered set D here and a subset X of this partial ordered set. Then an element D, this small d in large D, is actually an upper bound of this subset X if and only if all the elements in X is actually less than equals to D. Then we say this D is an upper bound of this set X. Okay, that means this D is larger than all elements in X. There can be multiple such upper bound. So among them, we are usually interested in the least one. So the least upper bound of X is smaller than any other upper bound of X. So we use this notation to represent the least upper bound of X. Okay, here are the same examples as before. Now let's focus on the least upper bound of each poset. So first, for a subset of this power set, for example, the empty set and Y. Let's take a look at this subset. What are the upper bound? Okay, there are four possible upper bounds of this subset. For example, this Y itself and YZ and XY and XYZ. Each of them is larger than Y and larger than the empty set. Okay, so among them, what is the least? Actually, this Y is actually the least upper bound of this set. Okay, and for another subset, if we take these two elements, XY and YZ, then what is the least upper bound? The least upper bound will be this XYZ. Okay, does that make sense? Let's take a look at the second example. So consider this subset that include the bottom and 0. Okay, what is the least upper bound of this subset X? It will be this 0. Okay, then another example, then let's think about this 1 and 2, this subset. In that case, there's no upper bound of this subset Y. Okay, so there is no the least upper bound also. Then next, if we take this example, if we take any finite subset of natural numbers like 0, 1, 2, then what is the least upper bound? The least upper bound will be actually the maximum of the integers in this set, which will be these two. Simple, okay? But for the set N itself, okay, which will be the set of whole integers, if we take this subset, actually the whole set itself, then what is the upper bound? There's no upper bound of the whole set of integers, whole set of natural numbers in this set. Okay, there's no upper bound in the set. The upper bound of this whole set of natural numbers makes sense if we add the infinity symbol to the set. Okay, so in this case, the upper bound of the whole natural number will be this infinity. Okay, the next thing we will talk about is chain. So for a certain partial order set D, a subset of X of D is called chain if X is totally ordered. Okay, totally ordered means that we can enumerate all the elements according to the order, which is a stronger condition than partial order. Okay, in partial ordered set, there might not exist an order relation between two elements, but in totally ordered set, there always exists an order for any two elements. So we can make a chain that visits all elements following the order. That's why we call this property a chain. Okay. So formally we describe the thing like this. Okay, then let's find chains in the same example. So in the first example, so let's take a look at the totally ordered subset empty set y, yz, and xyz. This subset. Okay, we can enumerate these elements, which means that we visit all the nodes following the order. Okay, so this is a chain. But if we take these two elements, then it does not make a chain because there's no relation between these two elements. Okay. In the second example, there are infinitely many chains. If you pick any number and bottom, then there is a total order set like this. Okay, so as you can see, there are infinitely many chains in the set. Next will be much simpler because this set, the set of natural numbers, is already a totally ordered set. So any subset of the set will be a chain. For example, 0, 1, 2 will be a chain. Okay, or 0, 100, 1000 will be also a chain because there is a relation, order relation. Okay, the same thing also happens in the last example. Then finally we are ready to define CPO, which means complete partial order. Suppose this D is a partially ordered set and there will be potentially many chains. Okay, this set D is a CPO if every chain X of D has this least upper bound, which is also in D. Okay, which is simple. So if a partial order set is a CPO, then this trivial lemma hold, which means that it has the least element, which is bottom always. Because the empty set is also a subset of the poset D, and the empty set is also a totally ordered set, which is a chain. Okay, then the least upper bound of the empty set is the empty set itself, which is already in the poset D by definition of CPO. Okay, that's why CPOs always have the least element bottom in the set. Then let's take a look at the same set of examples. Among these four posets, which one is CPO? Let's take a look at this one by one. So for the first example, there are many chains, as you can see. For all chains, the least upper bounds of the chains are in the set. We have to check this part. Okay. For example, for this chain, the least upper bound of this chain is actually Z, the singleton set Z, which is already in the set. Okay. For this chain, the least upper bound is this set, which is already in the chain, and so on and so forth. Okay, so as you can guess, all the least upper bounds of chains are actually in the set. So this is a CPO. The next example is much simpler. For all chains, which means that each set that only contains one integer and the bottom in this case. So the least upper bound is actually the integer. For example, this chain, the least upper bound is 2. For this chain, the least upper bound is 0. Okay, for all the cases, the least upper bounds are already in the set. So actually, this is also a CPO. So next, is this a CPO? So if you pick any finite chain, then the least upper bound of the chain will be the maximum element. So it is in the set, which is good. For example, if you pick this chain, the maximum will be 2, which is already in the set. If you pick 0, 100, 1000, then the least upper bound will be 1000, which is already in the set. Okay, so far so good. But for the largest chain, which means the set of all integer, all natural numbers itself, then what is the least upper bound of the chain? So there's no such an element in this set. Okay, so the set of natural number is not a CPO here. To make this CPO, we have to introduce an additional symbols like this infinity symbol and extend the order relation accordingly to support this infinity. Then finally, for all chains in the set, there exists the least upper bound, which is in the set. So this is a CPO.